Hi everyone and welcome to another video in Mr. Carroll's classroom. Today we're going to do some real-life trig applications and specifically with the tallest Ferris wheel in the world. So let's get started. Alright, so we're going to start by bringing up the place of interest, which is actually going to be the city of Dubai. So the city of Dubai is very well known for extravagant things and tall buildings and world records. And in this case, if you look all the way on the left here, there's actually that's the tallest building in the world, which I might butcher the name here, but it's called the Burj Khalifa. And the dimensions of this city, or I'm sorry, of this building is 828 meters tall, or 2,722 feet. So monster building there. Okay, now. And I don't know if it's already built, but I do know that, or if it's already finished, but I do know that in 2020, they are building the world's tallest Ferris wheel. So this Ferris wheel, in comparison, is going to be 210 meters tall, okay, compared to the 828. Now that might seem pretty small compared to, that whopping 828. It's about 25% of it. But really compared to the rest of the city, I mean, the highest point of this thing is way up there. And that's the whole point, right? So they want a lot of people to come and ride on the Ferris wheel. I think the thing can, I think I read that it can hold up to like 1,400 people, something like that, at any given time. There's going to be specific pods, like 12 different pods, where you can. It's basically a restaurant where you can have dinner and everything like that. So a pretty amazing thing there. So. All right, now this is a little bit small here. So what I'm going to do is I'm going to blow this up, and we're also going to get rid of our, let's see here. We're going to get rid of our skyline, and let's see here. Let's get rid of that, and let's get rid of our skyline here just because it's a little bit distracting. And so now we're back to our nice normal little chalkboard here, okay? All right, so let's bring up the Ferris wheel again. And so we're going to blow this thing up nice and big. And let's talk about the dimensions again. All right, so as I said, this thing is going to be 210 meters. And so Ferris wheels don't just sit on the ground. The circle doesn't just sit on the ground. So there's some kind of platform. I'm just going to go ahead and say that it's going to be 10 meters tall, our platform, which basically is 10 meters from the ground to the lowest point on this this circle. Okay, the reason why I chose that is because, well, if it's 210 meters tall and the platform is 10 meters, then that means the diameter of this circle is a nice even 200 meters to work with. Okay, so that's going to be kind of important for us. All right, another thing that is going to be important is going to be the timing. Okay, so this thing takes 45 minutes to make one complete revolution. All right, so let me go ahead and also talk very quickly about how we ride a Ferris wheel, in case you guys aren't familiar. So when you ride a Ferris wheel, you start at the bottom. Let me go ahead and draw on here. We start on the bottom. Right here, right? That's where we start, okay? And then we go ahead and we rotate around this thing, and after, well, let's just say after 90 degrees, okay, we are halfway up. In fact, we are even at that point in time with this center. Very important. All right. After another 90 degrees, we are now at the maximum of this circle, and then 180 degrees later, for a full 360 degrees, we are now back at that minimum. So the lowest point on the circle. So, and let's keep in mind it takes us 45 minutes to make one revolution. That's actually kind of important because let me go ahead and bring up these axes here. When I graph this thing, I am actually not gonna use the angles, right? Here I'm using radians for these for this scale, which you could use degrees if you wanted to. I'm actually going to convert this over to timing because this thing should take 45 minutes for one cycle. In other words, its period is going to be 45 minutes. All right. So now that we've kind of discussed, a little bit about what the dimensions are and the numbers and all that, we are going to talk about our candidates for for modeling this behavior. Okay, because ultimately we want to answer questions like, if you're on the Ferris wheel after 31 minutes, how high are you off the ground? Something like that. Okay. So let's go ahead and talk about the candidates. Now, there are, to model this, there are 6 trig functions, right? There's sine, cosine, tangent, and then there are all those reciprocal functions, which are going to be secant, cosecant, and cotangent. Now, right away, I'm going to throw out the reciprocal functions because the secant, cosecant, and cotangent, they all have vertical asymptotes where they go up to infinity and down to negative infinity. And yeah, that's impossible in the real world. Not only that, but we can't cross a vertical asymptote, which means that at that given point in time, we wouldn't even exist anyways. We would just disappear and then reappear. So yeah, that doesnn't model any, this particular case in the real world for sure. I'm also going to throw out the tangent, and let me go ahead and bring up the tangent graph, because this tangent graph, it also has vertical asymptotes, right? And it also goes up and down to positive infinity, negative infinity. So that's also out of the question here. All right, so what do we have left? Well, we really have the sine and the cosine graph. So let me bring up the sine graph. And yeah, the sine graph is actually a very good, or it has a lot of potential in this case, right? What makes it have potential? Well, it has a max, it has a min, it has this midpoint, right? That where we're kind of going along, or we're oscillating around this midline. There's no positive or negative infinities. There's no vertical asymptote. So yeah, this is a really, really good candidate. Okay. But if I bring up the cosine, I mean, it has all the same features, right? It's also a very good candidate. And to be truthful, you could use either of these. So let's talk very quickly about sorry, I just undid something. So let's just talk very quickly about the vertex form. So this is the sine function, but it doesn't really matter what you throw in here. What I want to talk about are the different numbers that we can change to transform these, right? Because we want to make one of these fit this situation. So over here, if I look at A, okay, this A represents a vertical shift or compression. Okay, it's on the outside of this middle here, so or this function, right? So it affects it vertically. So also, if the A is negative, it's going to flip this thing vertically as well, or reflect it over the x-axis. The K is going to be a vertical shift up and down, which we are definitely going to have to use actually both of these. Okay. Because A stands for amplitude and K is where that midpoint is, okay, or the midline. All right, so we can manipulate those. Now on the inside, the H is our horizontal shift, left and right, which we call a phase shift when we're talking about trig functions. Which, yeah, we'll talk about that in a second. We're actually going to try to steer clear from that because we haven't really practiced it yet. And then B, we use B to calculate the period, and so this represents our horizontal stretch or compression, and if it's negative, it also flips it. We're not going to worry about flipping it though in the horizontal direction, but we're definitely going to have to play around with B to make this match up with our period. What is the period? The period is how long it takes to go through one cycle, which in this case is 45 minutes. So that's going to be important to us, okay? So all of these can be manipulated, A, B, H, and K, so that way we can get either of these actually to fit. So, and what are either of these? Well, that's the sine and the cosine. So let's talk about the sine first as our candidate, and let's talk about the pros and cons about with using it. So if I go over to my Ferris wheel, remember we start down here at the lowest point, which corresponds to this point on my graph. Now, ideally, this point, right, should be at, given that our horizontal scale is going to be in time, it should be shifted over here. Right? It should be shifted over here. And then we're going to move it up to whatever point this lowest point needs to be. In fact, this needs to be 10 meters above. So so what is that going to involve, right? So it's going to involve a shift in the k, so we're going to have to do this plus k, but then also on the inside of here, we are going to have to take our angle, and we're going to have to do a phase shift. In fact, this would technically be 3 pi over 2, because that's how much we'd have to shift over, and actually it'd be plus 3 pi over 2 because we're going to the left direction. So again, I want to kind of steer clear of phase shift, so let's move on. And we're going to talk about the cosine. So let me undo all of this work that we just did, and let's bring up the cosine graph. Take away sine, bring up cosine. Okay, so pros and cons for cosine. Well, first of all, the cosine starts at the maximum, and we just said we want to start at the minimum, right? So that's a problem. Let's see here. What else is there? I mean, well, let's just talk about how we can actually fix that, because in my eyes, I see cosine as a really good candidate right now. And so why is that? Well, that's because what would happen if I just put a negative out front of here in front of the a? Well, what does that do? Well, it vertically flips this or reflects it over the x-axis, which means that this point that is the maximum, it's actually going to get moved down here to be the minimum. And everything's going to flip. So actually, it's going to look something like this. And let's just take a look and see, investigate this to see if this kind of fits our situation. So at time 0, this is t is equal to 0, right? At time 0, we start at the bottom. So that's good. We're starting down here, right? Perfect. We go to pi over 2. We're going to convert these over to time in a second. But we're going to go over 90 degrees. If I go up 90 degrees, right? Where am I at? Well, I'm at height 0 related to the center of this, right? And here we're at height 0. I go another 90 degrees, and now I'm at the maximum. Perfect, right? And this thing seems like it's following it very nicely. Another 90 degrees, it's going to be at 0 again, and then another 90 degrees, and we have gone back down to where we started right here. All right, and what I really want to do is make sure that this period is going to be 45 minutes. Okay, so it looks like the cosine is going to be a really good candidate here because it's not going to involve a phase shift. Okay, all right, so let's go ahead and we are going to go ahead and attempt to do this. So I'm going to get rid of all that work. I'm going to take away the cosine graph, and let's go ahead and start putting in these start creating our function here. Okay, so let's go ahead and start with I don't know, I guess I could call it f of x or y is equal to or whatever. Let's go ahead and give it a name. We'll call it f for Ferris wheel. How about that? And I'm going to use x here, and this is going to be equal to, and so just recall that we are definitely going to have a negative out front. This is going to be a times the cosine of, and we're going to have b times x. I'm going to take out the h for now, okay, because we're not going to do a phase shift, but we are going to have to increase this thing, do a vertical shift as well. Okay, so let's go ahead and do that. All right, so and yeah, let's hang on one second. I'm going to change in my axes. Let's go ahead and relabel these, right? This is not going to be 2 and 1. We're definitely not going to go by ones here. We are going to basically, let me see here. Let's see. I should really lower this thing, shouldn't I? Do I really want to erase this entire thing while we're doing this? Yeah, what the heck, why not? Actually, let's go ahead and pull off our axes. Let's make some more axes here. Because the issue with these axes, let me bring these back up, is that like we can go into the negatives, which would mean we're underground, right? And we're not going to go underground for this at all. So let's go ahead and redo these axes real quick here. So here we go. So here's my vertical, and here is my horizontal. All right, put my little arrows on there. Okay, so all right. So this question is like how high is this thing going to go? Well, it's going to go up to 210 meters, right? So that's going to be the tallest piece of this. So I'm just going to label kind of like what we're interested in. So this is going to be 210. And actually, let me put a little bit more room because I'm going to put my real function below this. So I'm going to put 210 here. Actually, let's do it right here. 210. All right. And what else am I going to do? I'm going to put 10 right here. I know this is not going to be exactly to scale. Okay. Which means that what is going to be halfway in between these, because technically that is my circle right there, right? That corresponds. This midpoint is going to correspond to this midline, or this midline is going to correspond to the height of this point here. So what is the height of that point? Well, I got 10 meters, right? I'm going up 10 meters, and then I'm going to go up how many more to get to this midpoint? How many more to get to this midpoint? This distance right here is going to be 200 meters. 210 minus 10. So the split in half, this is going to be 100 meters. So I'm going to go up 100 meters. So right here is going to be 100. Okay? So that's going to be my midline. And actually, let's go ahead and kind of put in a little dotted line here, because I just want that there as a reference, essentially. Okay, this thing's going to oscillate around this midline like that. Okay, and actually that just gave me a value. That midline is K. So let's go ahead and put that in here. So what color do we want to do here? Let's do like a bluish color. So I'm going to say plus K, which is 100 in this case. Perfect. So I have one value. All right. All right, let's do the next one. We actually know what A is. A is the amplitude, right? The amplitude is essentially the radius, right? It's the distance from the middle to the higher point, or really the distance from the middle to any point on this, whether it's up or down or whatever. So what is that distance? Well, we just said it's 100 meters. So A is 100 meters. It's hard to see. 100 meters. Hopefully I have enough room here. And we're going to use the cosine. And really, the last piece is going to be what goes inside of here. And let me just go ahead and put my equals f of x. Now, the one thing I did tell you is that we are going to also vertically flip this, which means the A out front is going to be negative. So let's put a negative in front of there. Okay, so so far so good. Let's go ahead now, and I can actually go ahead and label. Oh, I never labeled my x-axis, did I? Let's go ahead and label that x-axis here. I am using white, and so I'm going to go away from angles at this point in time, and I am going to let's go out like one full cycle here. Obviously, this goes on forever, but so this thing is going to start at 0, right? And the amount of time it's going to take, actually, this is a little bit long. Let's go out here. The amount of time it's going to take is going to be 45 minutes. So we'll say 45 minutes. All right, so let's see here. Let's go ahead and break this down in quarters, because that's what we always do with our trig functions. So half of 45 is 22.5. So we'll say 22.5 minutes. Let's label this as minutes. Whoops. Forgot about the E there. And this over here is going to be height. Okay. All right. And so I'm not going to label these, but obviously you would cut these now in half. What is that? 11.25, and then add another, 11.25 to this. So would that be 33.75? But I'm just going to I don't want to try to fit that in there. So I'm just going to kind of leave these as is. Okay. So let's go ahead and start this. So this is the cosine. So it's going to look like this horseshoe, but it's negative and it's going down by 100. Oh, you know what? I made a mistake. 10 plus 100 is 110, not 100. So let me go ahead and fix that real quick. Sorry about that. So this is 110. Get the right color. 110. There we go. Okay. So and let me fix my K over here. This is 110 as well. $110. There we go. Sorry about that. All right, but anyway, so let's go ahead now and start graphing this. So this is going to be negative 100, so it goes down 100. The amplitude starts below here, and this is the cosine. So I know automatically that it is going to, I know the shape, right? It's going to be this horseshoe where it's going to go like that, and then it's going to go up to the highest point at 22.5 minutes. So halfway through your journey, halfway through your 45 minutes, you're going to be at the highest point possible. So let's go ahead and connect to those dots. And then you're going to come back down to the midline here. Actually, let me go through like that, make it look a little bit better. And then you're finally going to go all the way back down to where you started at 10 right here. So let's go ahead and complete this thing. And of course, this thing is going to continue on forever. Like so. I'm not going to do the negative side because technically there's no such thing as negative time. Okay. Now, the one thing that I didn't fill in is the b here. What is this b? Well, I'm going to go ahead and use my formula to figure out what b is. So let's go ahead and we'll do that over here. So the period, we know that the period is equal to, for sine and cosine, it's 2 pi over b. Now, I don't have b. That's what I'm solving for. But I do know the period. The period is 45 minutes, which means that 45 is equal to 2 pi over b. And so how do I solve for b from here? Well, I'm going to multiply both sides by b. So b times b. Running out of room. But anyway, those b's are going to cancel, which means that 45b is equal to 2 pi. All right. And then I'm going to divide the 45 over. So divide by 45. So what is b? b is 2 pi divided by 45. So let's go ahead and put that in here. I'm going to change to a smaller writing so that way I can actually fit it. So this is going to be 45 pi divided by, oh, I'm sorry. I'm doing the wrong side here. It's 2 pi divided by 45. 2 pi divided by 45. All right. And so there we go. So here we have this final function that models this Ferris wheel in Dubai, the tallest Ferris wheel in the world. So how would I use this? Well, X is representing time. So if I got on this Ferris wheel and I stayed on it, for, I don't know, let's say 500 minutes, then I can just plug 500 in here and I will know exactly how high I am from the ground at that given point in time. Okay. All right, guys. So there's a real world application problem with trigonometry. It can be a lot of fun to do these types of problems. Really, these types of cycles exist all over us naturally, and you can do tons and tons of problems, not just Ferris wheel problems. You can do waves like the electromagnetic waves, visible light. The electromagnetic spectrum is visible light, X-rays, 5G, FM radio, AM radio. Those are all parts of the same thing, which is this electromagnetic spectrum. But anyways, anything periodic, sound can be represented digitally as waves, and so we can measure all the pitches, which are basically your different frequencies, which essentially are just different periods. So anyway, but this stuff, it just goes on and on and on. Basically anything that is cyclical in nature, you can use typically a cosine or a sine function. Choose which one you want because you can just shift them over to represent those situations. So hopefully you enjoyed this lesson, and I will see you in the next one. Take it easy.